Welcome to you all in my YouTube channel Express Mathematics. In today's video, I am going to explain you about three-dimensional vector or space vectors. Before starting, I want you to make sure that you please subscribe my channel if you have not already subscribed, so that I will be encouraged to make more videos, and also press bell icon so that you will be informed about coming videos. And vectors are very important topics in mathematics as well as in physical science. So I am explaining about vectors from some few days, and now it's the turn of the three-dimensional vectors or space vectors. Okay, so let's state one important relation of the space vectors. If vector A, vector B, vector C be three non-zero non-coplanar vectors and if x, y, z be three scalars such that xa vector plus yb vector plus zc vector equals to 0, then x equals to 0, y equals to 0, and z equals to 0. Okay, so here if vector a, b, c are three non-zero and non-coplanar vectors, then the sum of these three vectors to be 0, x, y, and z, these scalars must all be 0, otherwise it's not possible. Okay, so if this a, b, c are coplanar vectors, if they are in a plane, then they will be 0 if three vectors are like this. Okay, and they can be arranged by multiplying by some suitable scalars. They can be arranged to make a triangle. Okay, so they can be fitted in a triangle like this way, and this parallel to this one, and so parallel to this, and this one is parallel to this line, and so you can name this as A, B, C, and here AB plus BC plus CA, these three vectors will be equals to, okay, these three vectors sum becomes 0, or you can call this as vector A, you can call this as vector B, you can call this as vector C, then vector A plus vector B plus vector C equals to 0. Okay, so sometimes we need to multiply these vectors by some suitable scalars to form the triangle, and this direction also may be opposite one. At the time multiplying by the negative scalar, we can make in this direction, so there the sum will be 0. Okay, so in this way, if these three vectors are in a plane, they are coplanar, at the time it is possible for them to be, for the sum to be 0, even if the scalar quantity multiplying these vectors are not equal to 0. Otherwise, if they are scattered vectors, okay, that if they are not in the same plane, okay, so if the vectors, three vectors are like this way, scatter one, okay, so like this way, scatter one, not lying in the same plane, at the time it is not possible for them to be 0. So this is all about three-dimensional vectors or space vectors. Now decomposition of a space vector. Decomposition of a space vector. Okay, decomposition of a space vector. Okay, for the decomposition of the space vector, let's write a statement first. Any vector R in the space can uniquely be expressed as the sum of the three non-zero non-coplanar vectors A, B and vector C, that is vector R equals to x A vector plus y B vector plus z C vector, where x, y and z are, where x, y and z are scalars. Okay, any vector R in the space can uniquely be expressed as the sum of three non-zero non-coplanar vectors ABC, that is R equals to xa vector plus yb vector plus zc vector. These A, B, C vector are non-zero and non-coplanar vectors. Okay, so every vector we can express in this term. Every vector in the space can be expressed in this term, and this x, y, z are the scalars. Scalars means there can be some numbers. Now I will show you the proof in short. Okay, short proof of this without writing much language, otherwise the video becomes very lengthy. OA, OB and OC are three mutually perpendicular straight lines here. OA, OB and OC are three mutually perpendicular straight lines. Let OP equals to vector R. Okay, OA, this OA equals to, it is vector A. Let OA equals to vector A, OB equals to vector B, this OB is vector B, and OC equals to vector C. These are three space vectors, and let OP equals to vector R be a vector in the space. Okay, So this A, B, and C are these vector A, vector B, and vector C are three non-zero and non-coplanar vectors, and OP equals to R. It is the vector in the space. Okay, so now here, if we suppose this is as x-axis, this is as y-axis, and this vertical one, this plane as z-axis, this plane as z-axis, then there will be the space vector OP. This one is the this plane represents the space vector OP equals to vector R. Okay, so here this one plane is z-axis vertically. Okay, this is perpendicular with this edge of the copy, and this one is perpendicular to this, it is vertical one, and this is z-axis, this is x, y, and here is one vector, it is slanting one. Okay, so this represents vector OP equals to vector R. Okay, now this vector R representation we are going to show here, and this OA, OB, and OC are non-coplanar. So this OA, OB, and OC taken in pair determine the three planes. Okay, so three planes are here. This AOB is one plane, BOC is another plane, and COA is another plane. And now through P, we will draw plane parallel to this AOB. Okay, so through P we will draw plane parallel to this plane, parallel to this plane, and parallel to this plane. Okay, we will draw three planes, and these three planes chords OA at A dash, OB at B dash, and OC at C dash. Okay, and now let us denote this point by Q, and this by N, and let us join this. Let us suppose this point to be M, and let us join this O with this M, and this, let us join this C dash with P. Okay, all right, so now here in the parallelogram OA dash M B dash. Okay, this OA dash M B dash is the parallelogram. Okay, and in this OM vector will be OA dash plus OA dash plus OB dash. Okay, using parallelogram law of vectors. Not to make this video lengthy, I am not writing language in much detail. So this OA dash is collinear with this OA, so OA dash equals to some scalar times OA vector we can write. That means we can write here this equals to OA dash equals to x times OA vector plus OB dash we can write y times OB vector, because OB dash and OB, they are collinear, and this implies x times OA vector, it is vector A, plus OB vector is vector B. So OM vector equals to x A vector plus y B vector. Here we have used the parallelogram law of vectors. Okay, also in the parallelogram OM P C dash, using parallelogram law of vectors, what we can write is OP vector equals to this, in this parallelogram OMPC dash, in this parallelogram OMPC dash, OP vector equals to, we can write OM vector plus OC dash vector using parallelogram operator. OP vector equals to OM vector plus OC dash vector. And OM vector we have already found out, that is X A vector plus Y B vector plus OC dash is, this is collinear with OC, so some scalar Z times OC vector we can write for this OC dash. Okay, this XA plus YB for OM, and this is XA vector plus YB vector plus Z. OC vector, it is vector C. Okay, and this OP vector it is denoted by R. Therefore, vector R equals to, we can write XA plus YB plus ZC. Okay, and in this way, any vector R in the space can be expressed as the sum of three non-zero and non-coplanar vectors, vector A, vector B, and vector C. Okay, and we have to show that, now we shall show that, the relation is unique, only one relation, okay, fixed relation. For this if possible, let vector R equals to X dash vector A plus Y dash vector B plus Z dash vector C, where X dash, Y dash, Z dash are scalars different from X, Y, and Z respectively. Therefore, so this X dash A plus Y dash B plus Z dash C will be equal to this X A plus Y B plus Z C, because both are equal to R. Therefore, X A vector plus Y B vector plus Z C vector equals to X dash A vector plus Y dash B vector plus Z dash C vector. This implies, when it comes here becomes minus, so X minus X dash vector A, when it comes here becomes minus Y minus Y dash vector B, plus this also becomes minus when it comes here, and C will be common, minus Z dash C vector equals to 0. And since vector A, vector B, and vector C are non-zero and non-coplanar according to our statement, then these scalars must be equal to 0. Planar. So scalars X minus X dash equals to 0, Y minus Y dash equals to 0, Z minus Z dash equals to 0, and therefore X equals to X dash, Y equals to Y dash, and Z equals to Z dash. Hence the relation is unique. Okay, so the relation is only one, it is unique, because we have supposed different scalars X dash, Y dash, and Z dash, but they became equal to the previous scalar X, Y, and Z respectively. So the relation is unique, only one, fixed. Okay, so no other type of relation. So we can express as a unique relation R equals to XA plus YB plus ZC vector. Okay, in this way we have a unique relation for every vector R in the space in terms of other three non-zero and non-coplanar vectors, vector A, vector B, and vector C. Okay, in this way, we have discussed about three-dimensional vectors and then decomposition of vectors in the space. And not to make this video lengthy, that I have not written any details in a long way. I have explained it in short way and then proved it. Okay, so here in figure, here OM vector, this vector I have written as this is OA vector, OA dash vector plus OB dash vector I have written, and then this vector R, using parallelogram law of vector, I have written R equals to OM vector plus OC vector, and this OM vector value from here I have substituted, and then in this way we have proved it. So from figure it can be visualized in short in this way. Okay, thank you for watching. I hope that you found this video helpful, and if you have not already subscribed my channel, please subscribe it right now so that I will be encouraged to make more videos, and also press bell icon so that you will be informed about my coming videos. Thank you very much.